Radial conduction heat transfer through a hollow cylinder. So there is a hollow cylinder and the inner radius is R1 and outer radius is R2, and heat is transferred radially from inner surface to outer surface. The cylinder having a thermal conductivity K. The inner temperature of the cylinder is T1 and outer cylinder is T2, and T1 is greater than T2. So heat is transferred from high temperature to low temperature, and it is a function of radius. So and when we apply, these are the boundary conditions at R equal to R1, T equal to T1 and R equal to R2, T equal to T2. So since temperature gradient are existing along the radial direction, heat must conduct radially outward from inner surface of the inner surface cylinder at T1 to outer surface cylinder T2, as I told earlier. Unlike in case of slab, here the area of heat conduction will not remain constant in the direction of heat flow, because here the temperature area is not constant, because the area is like this, and heat is transferred from the smaller area to larger area. Here the area is not constant. Assuming steady state one dimension heat conduction with thermal conductivity K. At any radius r, area of the conduction is a equal to 2 pi r. ये लेंथ, एरिया कैसे निकालते हैं सिलेंडर का? एरिया ये होता है एरिया 2 pi r इंटू लेंथ ऑफ द सिलेंडर. ठीक है. अब then we apply Fourier law of conduction. So rate of radial conduction heat transfer, to simply Q is equal to, like for a case of slab, we wrote minus Ka dt by dx, but here the r is varying, so dt by dr. So then substitute value of a 2 pi rl here, and applying the boundary condition, q dr by r minus 2 pi kl dt. To maintain steady state heat conduction, q is not function of r. So here when it is at the inner surface, then the heat transfer is qr, and it is not a function of r, so the heat q is at radius r and r plus dr same. So the final equation of a rate of radial heat conduction come out 2 pi rl 2 pi kl T1 minus T2 and then R2 by R1. R2 greater radius final and R1 inner. T1 minus T2 2 pi kl. So the corresponding heat conduction and the corresponding heat conduction resistance offered by the hollow cylinder is T1 by T2 pi q is equal to L ln 2 pi r1 2 pi kl. Remember this. So let's read some notes. If the thickness of the cylinder is very small, that is R2 approaches R1, and if the conductivity of the cylinder is very high, example, very thin copper cylinder, the above conduction resistance can be neglected. Suppose that that thickness thickness is thickness is what is R2 minus R1. It is very small. So R2 approaches R1 and conductivity is very high. So the conduction resistance can be neglected. Suppose let's solve a question. The stainless steel tube TS equal to 9 kilowatt per meter Kelvin of 22 centimeter inner diameter and 5 centimeter outer diameter is insulated with 3 centimeter thick asbestos. Suppose that there is a cylinder whose inner radius is 2 centimeter and then outer radius is it is uniform. 5 is the outer diameter. Sorry, this is radius. So radius is 1. So diameter is 2.5. So radius is 2.5. So this thickness is radius. Suppose that radius 2.5 half 2.5 centimeter. So thickness is 1.5. There is a asbestos layer whose thickness is 3 centimeter. So radius is this radius is 2.5 plus 3 5.5. If the temperature difference between the innermost and the outermost is T1 and outermost is suppose that I assume outermost is T2. So heat transfer per unit length. So we read the formula earlier above. So and the formula is Q equal to 2 pi KL T1 minus T2 ln R2 pi R1. So the formula is Q equal to 2 pi KL T1 minus T2 upon ln R2 by R1. So here there are two resistance. One is between this one and other is this one. So when suppose I modify here only Q by L because in question asks rate per unit length. So it is the first resistance, then second resistance, and then R3 by R2. Is it right? So this is the same. So here Q so 2 pi KL resistance, and then R2 pi R1. Just a second, one thing more, that the conductivity of both material is different. So note this one, and then R2 pi R1, 2 pi K1, पहले वाले के बीच K1, 2 pi K2. K2 is for asbestos and K1 is stainless steel. So this is steel and this is asbestos, and the answer come out to be correct for unit 10. So if K steel is very much greater than asbestos K value, so we can neglect resistance of asbestos because it is 19, here K, it is K not. Then radial conduction, heat transfer through a hollow sphere. So for a hollow sphere, so there is a difference in area. Area of sphere is 2 pi 4 pi r square, 4 pi r square. So radial conduction heat transfer through a hollow sphere. It is a function of r, and the inner radius temperature is T1 and outer radius temperature is T2. So heat is, in this case also, heats flow radially from inner tube to outer tube. So as we know that the object which supply heat, that is called, any body which supply heat is called source, and we absorb heat, it is called sink. So here let's read some important points. Since temperature gradients are existing along the radial direction, heat must conduct radially outward from the inner spherical surface T1 to outer surface T2, because here heat is transferred radially. So and the temperature of inner surface is T1 and outer surface is T2, like in case of cylindrical heat transfer. Here also the area of conduction heat transfer in the direction of heat transfer changes in the direction of heat flow. Here also area changes at any radius r, area of conduction heat transfer 4 pi r square. Fourier law of conduction, rate of radial conduction heat transfer, Q is equal to minus K A dt by dr. Q is equal to minus K, substitute value of A 4 pi r square dt by dr. Then integrate it over R1 to R2 and temperature T1 by T2. Assume steady state. So this equation comes for steady state one dimension heat conduction heat transfer with constant K. To satisfy steady state heat transfer condition, Q is equal to F. Q is not function of Fr. Because it is not function of steady state, means it is not function of time. Q equal to R plus dr. Q is equal to R. When we integrate and substituting the boundary condition, the final equation comes out to be 4 pi K T1 minus T2 R2 minus R1 and in multiplication R1 R2. So write in this form, Q is equal to T1 minus T2 up R2 minus R1 4 pi K R1 R2. So this is the thermal resistance. R2 minus R1 4 pi K R1 R2. A composite hollow sphere with steady state internal heating is made of two. In this, there is a hollow sphere with a steady internal heating is made of two layers of material of equal thickness with thermal conductivity. With thermal conductivity in the ratio of 1:2 for inner to outer diameter is what is the ratio of the temperature drop across the inner and what is the temperature drop पूछा है. So let's a composite hollow sphere with a steady state internal heating is made of two layers. This is the diagram and it is made up of two layers. Then of equal thickness. Both layers have equal thickness with thermal conductivity K1. Two layers in 1/2 and for inner diameter in T1 by D2 is equal to 0.8 or R1 by R2.8. The thickness are equal, so R2 minus R1, R3 minus R2 are equal. So thermal resistance between the layer T1, T2, T3 resistance R2 minus R1 R1 R2 R3 minus R2 4 pi K2 R2 R3. Rate of radial heat transfer Q T1 minus T2 R2 minus R1 4 pi K1 R1 minus R2 and T2 minus T1 R2 minus R1 right formula because Q steady state condition heat is transferred equally. So what ratio of the temperature drop across the inner to outer? Inner से outer. Inner T1 temperature drop this one. So in this diagram we show some temperature distribution. So this is the slab, this is the hollow cylinder, this is the hollow sphere. In slab linear temperature T1 minus T2 K is equal to constant. If K is not constant and K value is 1 minus alpha T, then it is linearly but not constant. Not linearly but quadratic 1 minus alpha T, and then alpha is equal to 1 plus alpha T. Then for hollow cylinder it forms logarithmic profile and for sphere hyperbolic. Arithmetic, logarithmic, linearly. Hyperbolic, logarithmic and linearly, and it is different. Only here area A of heat transfer remain constant in the direction of in the case of slab the area remain constant in the direction of heat flow. Consider one dimension steady state heat conduction without heat generation and there is no generation in a plane wall. The boundary conditions are shown in figure. boundary condition, the means the profile is k naught, k equal to k naught 1 plus beta t, where k naught and b are positive. Okay, this one and this one are positive. As x increases, the temperature gradient of wall. When we increase the x, how the temperature dt by dx vary. So write down k is equal to k naught bt. q equal to ka dt by dx Fourier conduction form. Substitute the value of k plus bt. So for steady state, it is mentioned that it is the log function of x, means it is inside also, like everywhere from t1 to t2, or we can say that within the slab the temperature distribution are the same. So rate of heat transfer is same. So q not function of x, a is not function of x for the case of slab. So this one is constant, this one is constant. So q by a is not function of x. So if k vary and dt by dx, so and k plus bt, if b increases, so this one is decreases to make constant. So and if x increases, then t increases, and so ask if x increases, the temperature gradient will increase. If x increase, temperature will increase. The cylindrical cement tube of radius 0.05 centimeter and 1 centimeter has a wire embedded into it along its length. To maintain a steady temperature difference of 140 degrees centigrade between the inner and outer surface, a current of 5 ampere is made to flow into the cylinder wire. Again, resistance of wire is 0.1 ohm per centimeter of length. The thermal conductivity would be cylinder and cement tube जिसका radius है 0.05 and 1 centimeter has a wire embedded along its length. To maintain a steady temperature difference of 140 degrees centigrade between the inner and outer surface, current दिया, resistance दिया, तो this also comes for steady state cylinder Q is equal to VI और I square by R, I square R. तो Q की वैल्यू दिया है यहाँ पर, ठीक है. डेल्टा टी भी दिया, हमें K फाइंड करना है और इनर और आउटर रेडियस भी दिया है. Radial conduction convection heat transfer through a composite cylinder. If there means convection, as we studied of the for the case of the slab, that there is both conduction and convection heat transfer occur for the case of the slab. So for cylinder case also, if same thing happen for the cylinder also, so same thing, we can follow the same procedure. So assume steady state one dimension conduction convection heat transfer between hot gas inside at Tg and the colder ambient temp air at T infinite. So in the similar way, we use thermal circuit procedure and then rate of a radial heat transfer. This is the formula. Defining overall heat transfer coefficient based on inside convection heat transfer area and overall heat transfer coefficient U naught based on the outside convection heat transfer area from the equation. We can write it in overall heat transfer coefficient. So QI delta T, U naught A naught delta T, and we can write the formula 2 pi R1L Tg minus T finite or U naught 2 pi R2L Tg minus T infinite. So when on substituting the value, the final equation or final value of overall heat transfer come out to be like this. In this equation we can in this equation this is one equation number 1 and this is equation number 2, and we can compare both equations. So but in heat exchanger analysis where LMTD method effectiveness and TU method you can calculate as neglecting conduction thermal resistance of pipe material without falling. So this has come out to be 1 by H1 and H2. When we consider the case of LMTD method effectiveness and TU method as this chapter you may learn in your bachelor's degree. So in that case 1 by U overall heat transfer coefficient is 1 by H1 plus 1 by